Yeah. Good morning, dear students. We have our next topic here from module 2, that is Gauss law. What is a Gauss law? Gauss law is the result of Faraday's experiment. We call it as about concentric spheres, charged concentric spheres, we call it as. So it goes this way. The result of Faraday's experiment with the concentric spheres could be summed up as an experimental law by stating that the electric flux passing through any imaginary sphere surface lying between the two conducting sphere is equal to the charge enclosed within that imaginary surface. I repeat here, there are two concentric sphere. Imagine two concentric sphere. So we found that sphere 1 is also a conducting sphere, sphere 2 is also a conducting sphere. Between these two concentric sphere, you have to imagine one more sphere. So, we say that here, the number of electric flux lines which leaves that imaginary sphere which we have between the two concentric sphere is equal to the charge enclosed inside that imaginary sphere. So this is what an experimental result of a Faraday's law. So Gauss law is based on this Faraday's experimental law. We call it as that says that the electric flux lines which leaves the closed surface is equal to the charge enclosed. I repeat, here we have an equation that is psi equals q, where psi represent the flux lines crossing the closed surface is equal to the charge enclosed. So very simple theory here. So in a closed surface, if you are having a number of charge, say q number of charge, then the number of flux lines which leaves the closed surface, electric flux lines which leaves the closed surface, will be equal to the charge itself. So Faraday's experiment can be generalized to the following statement, which is known as Gauss law. So now we are going to give a Gauss statement now based on the Faraday's experiment law that says that the electric flux line passing through any closed surface is equal to the total charge enclosed by that surface. Okay, I repeat the Gauss law here. So if you are having any closed surface which is enclosing an amount of charge Q, then the flux lines which leaves the surface will be equal to that. That is what the Gauss law we have here. The statement also given here. So this is about the Gauss law. Now imagine here distribution of charge shown as a cloud of point charges surrounded by a closed surface of any shape. You can take here any shape here. So randomly some shape has been taken here and you could see that it is enclosing some amount of charge. Now the total charge Q, the Q coulombs of electric flux will pass through the enclosed surface. Okay, I repeat, in this closed surface, if you are having Q the amount of charge, then the flux lines which leaves this closed surface will be equal to this charge Q. Now at every point on the surface, the electric flux density vector D will have some value ds. Correct. So we found that this is a closed surface. Correct. This is the closed surface. In all the 360-degree, you could see that the ds vector, or the flux lines coming out. So now we are going to specify a point here. Randomly, you can choose a point on this closed surface, and you have to identify a small surface here. We call it as differential surface here, and you will see that in this surface we will be having a flux line coming out that is having a value ds. Okay, so if ds is coming out for a small region or a point be considered here on this closed surface. Now this small differential surface is a vector, and you can imagine a vector here which is a perpendicular to a point p, perpendicular to the point p. Then we can say that the flux lines which is crossing is ds into cos theta, ds into cos theta into ds. This is what the differential flux which is coming out from this differential surface. I repeat here, we are now trying to understand the Gauss law. Gauss law says that in a closed surface here, if you find some amount of charge Q present, then that is equal to the number of flux lines which is coming out of that closed surface. Now, we are not considering this entire closed surface. We are considering a very small surface. I call it as a differential surface delta S. For a differential delta S, if you are considering it, you will be getting a differential flux. You will be getting a differential flux. That differential flux is equal to ds, that is amount of flux lines coming out of that differential surface, into cos theta. Why we are having cos theta here? Because this is a normal drawn to the surface what we have chosen here, and you will see that this flux lines can come out of a point in all the 360-degree direction. It can be having a value 0, as well as it can have a value that theta can be equal to 0, or theta can be equal to pi by 2. So, or what we call it as 90 degree. It can be 0 or it can be 90 degree. So here theta can become 0 or 90 degree, because we don't know in which direction it is coming out. The possibility of this ds is anywhere from 0 to 90, we call it as. So theta can go from 0 to 90 here. So this ds into cos theta multiplied by the ds, that is a differential surface we have in the vector form, is it looks like this. So this is what a dot product we have. So ds dot delta s is what the differential flux we have here. So now if I want flux from the closed surface, that is from the entire this closed surface, if I want the amount of flux coming out, then I have to integrate this differential flux. So I should compute here closed surface integral of ds dot ds. What is ds? This is a differential surface we have here, and this is what we have, the amount of flux lines in that small differential surface. So from the small differential surface, whatever the flux we are getting it, we have to integrate that over this entire surface. That's what the meaning we have to get the overall flux line. So we can say that now psi is equal to the closed surface integral of ds dot ds. This is the differential surface. This is what the flux line only from that differential surface, which is equal to charge enclosed, which is equal to q. This is how we represent Gauss law here, and we found that this holds good, or this is true only if you are having a point charge. Then you will see that q is equal to summation of qn. If your charge is a line charge, then your q will be integral of rho l into dl. If your charge is a surface charge, then it is a surface charge density into ds integral of closed surface integral, and q is equal to integral volume integral of volume charge density into dv. Remember here, as your type of charge here it is changing, you will see that this equation changes accordingly. So only the q here it is changing. So point charge, this is fine. We will be having ds into ds here, whereas line charge we will be using, and into dl we will be doing a integral, line integral, surface integral, and volume integral we will be performing as the uh, type of charge changes. So that's what we have given here. That is a charge enclosed meant by the formula above. Might be several point charges, a line charges, a surface charge, or a volume charge distribution. As I said, the charge distribution type changes. You will see that the Q representation here we will be changing. So here we are trying to define what is E and what is D here. So this is one more way of representing a Gauss law, we call it as. We now take the last form, I can say, written in terms of the charge distribution to represent the other forms. Just one more form we are trying to write here. So you have to imagine here a sphere of uh, radius as small a, that is radius r is equal to small a, and we are taking here a differential surface ds. differential surface ds, and in the vector form, the differential surface, that vector will be in this direction, that is going away from the surface. We have to take a normal to this surface. This is what the ds vector we have, that is differential surface here we have in this direction. Now, this is what the angle theta we have. This is what the angle phi we have. We know that elevation angle and the azimuth angle in a spherical coordinate system. So we have a coordinate theta here. We have a coordinate phi here. Now we need to find out the area of this differential surface. So I have to find out two lengths here, this length and this length I have to find out, and I have to multiply these two to get what is ds. How can I do that? In a spherical coordinate system, we have this line. This line is the radius here, which is A, the radius into d theta, change in the elevation angle. So change in the elevation angle, if I take it as d theta, the d theta multiplied by the radius, which is A into d theta, I get this length. What is this length? This length I'll be getting by multiplying by we will be getting that by multiplying sine theta into d phi. So I'll be getting that sine theta d phi into r. Okay, I repeat here. So this length I'll get it by multiplying the radius of this sphere into the change in the elevation angle happening between these 2 points. So I call it as d theta. D theta into A is what this length we have, which is also an arc, remember. And here this is what we have, again an arc. Since it is a sphere, this will be an arc. This arc is having a equation. This arc is having a equation which is A, that is radius, into sine of the elevation angle sine theta, into what we have, the change in the azimuth angle, that is angle phi. Whatever the change we have here, that is the small angle you can make out here, the angle what we have here, this is what we have d phi. So I can write now a ds vector, the differential vector, as a square sine theta d phi. That is, I am multiplying this both the side to get what is ds. And we know what is ds here. If you are having a charge q at origin, then I can write ds, that is a vector or flux which is coming out, is equal to q divided by 4 pi. This is a Coulomb's law here. Coulomb's law state that what is the electric flux density, that is what we have, q divided by 4 pi a square into ar, where ar is a unit vector in this direction, where a is the distance uh, between this differential surface and the charge here we have. So we have to multiply ds into ds according to the equation. We are going to get this. So psi, that is according to Gauss law, that is flux lines coming out, is a closed surface integral of, we have just calculated what is the amount of flux lines coming out of this ds. Now I have to extend this to entire sphere. So I have to do here closed surface integration. So closed surface integration of this ds, which is coming out by the small differential surface considered, if you integrate over the surface, closed surface here, you will get to know what is the total flux lines coming out. So you will be having surface integral, means you will be having two integral, where the azimuth angle is changing from 0 to 2 pi, that is one complete round of a sphere. And theta, we know that it is ranging from 0 to pi. So elevation angle is ranging from 0 to pi, and the azimuth angle is changing from 0 to 2 pi, so as to complete a sphere. Then I have to now take ds into ds, that is what we have calculated here, q divided by 4 pi sine theta d phi. Now flux line phi is equal to minus of q divided by 4 pi sine. If you integrate, you will be getting cos theta, and applying the limit of theta, that is 0 to pi. And d phi we have here, if you integrate this d phi, you will be getting phi. There is a print error here. Please My apologies. Here, theta, you should make it as phi, and this phi is ranging from 0 to 2 pi here, and we will be having a Q here. So we say that the flux line phi is equal to the charge enclosed. You can see that after substituting these limits, you will see that phi is equal to Q. That is what Gauss law is all about. Thank you. We will continue with this in the next video.